Hello, good people. Welcome to the first video of our volume section. We're actually going to start volumes with 8, 8, and 8, 8.7 and 8.8, and then we're going to go back, excuse me, and we'll pick up the other types of volumes. But I feel like if you understand volumes by cross section, then everything else is going to make sense. And the idea behind volumes by cross section is a pretty basic one. And so I will say that this first sentence, we really haven't talked about volumes generated by revolving a given region around a horizontal or a vertical axis. Um, we haven't gotten to that yet. That's coming after this set of videos. And so we've only done areas. But the idea behind volumes of cross section, I think, is pretty basic, and it's pretty applicable. I'm looking at two loaves of bread, but someone has taken these loaves of bread and slice them up. Now, if you look at these slices, the slices have a similar shape, even though they're not the same size, right? Like this slice of bread is similar to a slice of bread over here at the end, but they're not the same size. However, they all have the same shape for the most part, right? And so the idea is if we know what the cross-sectional shape is, if we know what the shape of the slice is, a cross section is just a slice. If we know what the shape of the slice is, then what we're really doing is just finding the area of one of those slices and then adding a bunch of slices together. And if you remember the definite integral, when we started the definite integral, especially with the Riemann rectangles, we said we're going to build some rectangles that approximate. Oh, but we can build more rectangles and add them together. Well, if we add an infinite number of rectangles, then we're going to get the full area under the curve. Well, the same idea here. I can start by saying I'm going to take one slice and find the area of one slice. But what if I stack a bunch of slices together? What if I stack an infinite number of slices together within a given window or interval? Then that's going to give me the full volume. And so I know Brian does a good job of giving us some examples here, some visuals. Here I have four three-dimensional shapes that are created by cross section. If you look at the green one, this is made up of cross sections that are semicircles. If you look at the blue one, this is made up of cross sections that are rectangles. If you look at the yellow one, this shape is made by creating cross sections that are triangles. And then if I look at this purple one, this is created by cross sections that are squares. However, what we want you to see is that the base of all of these shapes is the same. We're using the same function, whether it's the green three-dimensional object or the purple or the yellow or the blue three-dimensional object. The base is always the region trapped between the x-axis, y equals x squared, and 1. However, depending on what type of cross-section I make or I use, well, then I'm going to create a different three-dimensional object. And the idea here is that these are objects that we don't have volume formulas from geometry, right? We know how to find the volume of a cone and a sphere and a cylinder and all those geometrical shapes. These are non-traditional shapes, and yet they still have volume, right? And so we're trying to figure out the volume of these non-traditional shapes, knowing that their cross sections, that their slices are all similar shapes. So as we go on with this video, let's remember the calculus is always requiring us to create one small piece of whatever we want to know. And then by using the definite integral, we accumulate or we add all of those tiny pieces. So the definite integral is the accumulator or the sum, an infinite sum of those pieces. So the key to doing these types of problems is to figure out what's the shape that's the cross section, that's a slice. Do I know the formula for the area of that shape? Can I create an area function? And then let's integrate the area function, because again, when I look at these, if we focus on the green one here, if I look at these, they're all semicircles, but obviously the semicircle on the end over here is bigger than the semicircle at the beginning. So I can find the area of one semicircle if I know what the x value is. But what if I want to find the area of any semicircle? Well, then I need an area function. And if we integrate that area function, we're going to get the volume of that shape. Okay, So a couple of things. Whenever you read an AP problem that has to do with a volume by cross-section, they're going to tell you to find the volume using a definite integral. So we're going to practice setting up definite integrals to do that. Our representative rectangle will act as the base of whatever shape that we're using, right? Because if you think of standing up a slice, the slice has to have a little bit of width, right? So that base is going to be where I'm going to put the slice or cross section. Our rectangles will always be perpendicular. They're always going to use that phrase, perpendicular to either the x-axis or the y-axis. So if you look at perpendicular, yes. So if you look at your paper and these examples, notice that all of these shapes are perpendicular to the x-axis. They make a right angle with the x-axis. Sometimes they'll ask us to make three-dimensional shapes that are perpendicular to the y-axis. They'll make a 90 degree over here. But right now, the ones that we're seeing here, this is the x-axis. This is the way the shape is. So it's making a 90 degree angle with the x-axis. But they're always going to designate which direction they want us to put it. We simply need to find the area of the given cross-section using our representative rectangle. Representative rectangle. And some problems, sometimes they're nice, and some problems simply give the area function without giving us the shape. And so sometimes that kind of makes students a little anxious because they usually start by thinking, what is the shape of my cross section? But sometimes they advance that thought process and give us the area without giving us the shape at all, and we can still figure it out. So in this video, I just want to go over the steps that we're going to need in order to find the volume of a cross section, remembering that we are taking a representative rectangle that's going to act like the base of that slice. We're going to find the area of that slice shape. We're going to convert it into an area function and then build an integral of that area function so it can accumulate or add an infinite number of those little slices and create a full three-dimensional object. Okay, let's see. So the first thing we're going to do is we're going to draw the representative rectangle. Perpendicular to the given axis. So they're going to tell us perpendicular to the x-axis, perpendicular to the y-axis. Drawing this is going to help us think about how we're going to orient it, what kind of limits we need. We're going to set up the integral as follows. We're going to go from the integral from a to b, but remembering a and b could be x values if it's perpendicular to the x-axis, or a and b could be y values if it's perpendicular to the y-axis. And we're going to take the integral of the area of a cross-sectional shape. We're going to find the formula for the area of the given cross-sectional shape based on our representative triangle, or representative rectangle, sorry. Remembering that the height and the length of the rectangle is always the base of that shape that we're using, right? And then we're going to write our limits of integration. This is what I was telling you. These numbers, oops, let me use a different color. These numbers, the limits of integration, you got to make sure, are they x values or the y values? Depending on what the cross-section is perpendicular to, that's going to tell you what type of values they are. And then finally, and this might seem silly, but is it asking you to just set it up, or does it want an answer? Because you're going to find that a lot of times, because this is a time test, they really don't want you to spend the time finding the answer. They just want you to set it up. And if you set it up correctly, bam, you just earn some points right off the bat. So in the next video, we're going to look at a specific example. It's going to be actually from 2000, from A/B test, and it's number 1 from the year 2000. We're going to walk you through the process, and you'll be able to set it up and solve it with no issue.